have you here, Cédric.
All right. Thank you very much. Bom dia, everyone. Thank you, Professor De Oliveira, for the invitation. I'm very happy to be here. I understand that there are mostly students, different levels, very good. So don't hesitate to interrupt and ask questions. I think it's much better if we can have some interaction. Let's go to full mode. Okay.
So just one more thing. If you want me to translate the question, if you want to ask in Portuguese, the students want to ask in Portuguese, I can translate. Então, se vocês quiserem perguntar em português, eu traduzo para ele, tá bom? E ele diz que pode fazer perguntas durante a apresentação.
Okay, thank you very much. So, okay, a little bit of context. So basically, I'm very interested in the hadron structure. So basically, understanding the properties of bound states of quarks and gluons, so basically in the non-perturbative regime of the strong interaction, QCD. And there are many questions that are somehow hot topics for now several decades. For example, understand how the spin of the nucleon comes about, how it is decomposed into the quark spin, gluon spin, the orbital motion of those particles. And another aspect that has regained interest in the last 5 years, basically, is the question of how to decompose the mass of the nucleon, for example. And that revived old ideas, basically, that there were at least 2 ways that were proposed to decompose the mass of the nucleon, but it was not clear how those two pictures were related to each other. And among the discussions, there were many times the concept of Virial theorem that was invoked, and it appeared that people had a different idea and understanding of what the Virial theorem is. And so in the work here that we recently published 2 years ago with my colleagues from the US and Italy, we kind of reviewed the concept of Virial theorem from different domain in physics, and then move on to the particular case of quantum field theory, which is the relevant one for the question of the nucleon mass decomposition. And once we understood exactly what is the Virial theorem, then see what is the implication for the nucleon mass structure. So outline is very simple. First is what is the Virial theorem? Second, what is its physical meaning? It's good to have a physical understanding of the statement that is given by the Virial theorem. And then what is the relation to the mass? So the Virial theorem is really an old story. So if you look, essentially the idea was proposed in the late 1900s, 19th century by Clausius. What we're doing is actually thermodynamics and so on. So imagine that you have a classical system made of classical points, like here. You have many points. Can you see my cursor, the mouse?
Yes.
Yes. Okay. Very good. And then for each of the particles, you have a certain momentum attached to it. And then the total momentum of the system is just the sum of the momentum of the individual particles. And then you have some kind of orthonormal system, and you can define the position of the particles with respect to that system. And then you can define a weird quantity, somehow, what's called quantity G. We'll see later what it means, actually, but here it's just a simple construction. Just consider the scalar product, the projection of the momentum along the position, or vice versa, the position along the momentum, and you sum of all the particles and you get a certain quantity. And if you start from that quantity and you look at the time derivative of the quantity, then you will have 2 terms by the chain rule. If you differentiate the position, you get the velocity. So the first term will be the scalar product of the momentum by the velocity of the particle. And the second term will be the time derivative of momentum, which is by definition the force acting on the particle. And so you get the scalar product of the force acting on the particle and the position of the particle. So that's just math. There's nothing more than that here. The interesting thing is that if you consider the system over a long time, and then you average over the time, so basically you look at a quantity, you integrate over time, and then you divide by the time span, the time range. And then you take the time range, the time window to be infinitely long. Well, if you apply this, you take the time average of the time derivative, it just at the end corresponds to taking the initial value the final value, you take the difference between the two, you divide by the time window, and you take the time window going to infinity. And so what happens for bound state essentially is that for bound state, the particle cannot be anywhere and cannot have any momentum because you have a constraint. They have to be somehow confined in some region. And then it is expected that the difference here is finite, even for any value of tau, while tau goes to infinity. So the result of this, the average over time of this time derivative should be 0 for bound state. So really, the very first application of Virial theorem, it was for bound states. And what does it mean? So if the time average, so the average over time of this quantity is 0, it means that you can equate the time average of this quantity on the left-hand side, on this side of the first term on the right-hand side, and the time average of the second term. And if you look at the scalar product of momentum and velocity, and remember that for classical particles, the momentum is essentially the mass times the velocity. Well, this scalar product up to a factor 2 is essentially the kinetic energy. So you find at the end that the time average kinetic energy is related to the time average of the scalar product of the force and the position of the particle. And this quantity is called the virial. So the origin of that name is because in Latin, virial means force, energy, power. It's just a name that's closely proposed for this kind of scalar product. So if we can essentially identify the forces that are acting on the system of particles and look at the time average of all the configurations, basically you get via the VR theorem an expectation value of the kinetic energy of the system. And now imagine that the particles are basically interacting via some potential force, and the potential is a power-like form, essentially the difference of distances between the particles, for example, raised to some power n, while the right-hand side of virial will be essentially something that is proportional to the average value of the potential times a factor that depends on the power of appearing in the potential. So the Virial theorem at the end, in this very specific case, is the relation between the average value of the kinetic energy and the average value of the potential energy. That's basically what it tells us. So far, so good?
Yes.
Yeah. Okay, go. Okay, so that's classical point mechanics. So what can we do with that? Well, the very nice thing is, for example, to consider a gas. So a classical gas where you have point particles that are bouncing inside a box. So now imagine that you have a box. So we have hard walls all around here. And we consider, in this case, an ideal gas, essentially a gas or a perfect gas without mutual interaction. So the only interaction is with the walls where the particle is bouncing on the walls. So the only forces that the particle will feel are essentially the walls on the container. And when you have lots of bounces on the wall of the container, that is what we usually interpret as the pressure of the particle on the walls of the container. So we can re-express this virial essentially as the pressure that we assume to be constant everywhere. So everything is at equilibrium. And then the pressure is the force per unit surface. You multiply by the element of surface and you integrate over all volume. And for each of these elements, you multiply by the position R of the element on the boundary. Then what you do, since the pressure here is constant over the volume, you can remove it from the integral. And you use essentially the Gauss law to transform a surface integral into a volume integral, which leads you at the end the divergence of the position, which is just a factor 3. The integration over the volume just gives you just the value of the volume, and then you get at the end 3/2 of pressure times the volume. So it feels already kind of familiar here. So this is the value of the virial. The Virial theorem tells you that, therefore, that the average kinetic energy must be the virial, which is 3/2 PV. And then you can use another theorem, which is called the equipartition theorem, that basically attributes 1/2 kBt average energy to every kind of degrees of freedom that you have. Here you have n particles. They are moving in 3 different directions. So you have 3 n times 1/2 kBt for the average kinetic energy that you expect. So now if you equate those two expressions, what you get is just the perfect or the ideal gas law, PV equal NKBT. So with the Virial theorem, it's a very nice way to get a familiar formula that you have probably encountered before. So that is classical physics. You can do something similar in quantum mechanics. So in quantum mechanics, we still have a bunch of particles. You will attribute some momenta operators. You can still define the position operators, and you can define the momentum operators before. Just now they are operators. You can also define the quantity G that becomes an operator, just defined by the scalar product of momentum operator and position operator. And you can, and if you are interested in the physical values, you have to take the expectation value in the state of the system. And the Ehrenfest theorem tells you basically that the expectation value of your operators basically satisfy the classical laws. So the time derivative of the expectation value of the operator G can be also obtained as the expectation value of the commutator of G and H, because H tells you how the system evolves in time. In other words, the Hamiltonian generates time translation that tells you how the system evolves. So for typical quantum mechanical system, non-relativistic quantum system, we have the typical kinetic energy operator and then some potential operator that depends on the position of the individual particles. And if you calculate the commutator of this Hamiltonian operator with the quantity G, using the fundamental commutation relation between position and momentum, well, you get something that is very similar to classical mechanics. You get twice the average value of the kinetic energy, and on the right-hand side, since the momentum operator turns into a partial derivative with respect to R when you work in position space, and then you take the average value of this guy. So now what happens in quantum mechanics? So we will be, for example, interested in normalizable stationary states. Essentially, we look at eigenstates of the Hamiltonian with some fixed energy. And in that case, for this kind of states, well, if you calculate the commutator in that state, you will automatically get 0, because when H acts on the right-hand side, you get the energy. If H acts on the left-hand side, you get, again, the energy, and so the difference will be 0. So which means that if you use normalizable stationary states, the time derivative of the expectation value of the G is simply 0. So something similar to classical mechanics, which we simply do not need time average, we just need expectation value in a stationary state. But you get essentially the same kind of answer. And then in quantum mechanics, the Virial theorem is just, like in classical mechanics, some kind of relation between the expectation value the expectation value of the kinetic energy and something that is related to the potential. And again, if your potential is something that goes as the difference of position to some power n, it's essentially proportional to the expectation value of the potential times a factor. So what happens if your system is not stationary, but is a superposition of stationary states, which gives it some time dependence? Well, in that case, you can apply the same thing, and you just have to do like in classical mechanics, on top of the quantum average, you take also the average over time, and you still get 0 for a bound state. And what is also important to note is that for the stationary state, we need the system to be at rest. So for example, if you take the operator would be the average, the position of the center of mass of the system, well, the velocity of the center of mass should be 0. So essentially, when you apply the Virial theorem, you really have to think of a system that is in front of you and with 0, in average, 0 velocity. It's not a system that moves with constant velocity in some directions. And when we think in terms of a bound system, we always think usually in that situation, you have a bound system, you go in the center of mass of the system, and the center of mass is at rest with respect to the observer. So you see, these are already kind of old stories. And in quantum mechanics, people realize that we can have an understanding of this quantity G that is more kind of a geometric operation. Actually, people notice that this particular combination of position and momentum operators generates what we call spatial dilatations. So, for example, if you exponentiate this operator, so you take the exponential of the operator times some constant, just like a Lie operator, and you do a transformation of the position operator, where you realize that you get the position operator, but that will be rescaled by a factor lambda. Lambda is just related to the factor kappa here. So it's basically a rescaling of the position of the particle. And if you use the same transformation on the momentum operator, then you have a scaling, but in the opposite direction. So basically, you inflate the system, so the sizes increases, but the typical momenta have to decrease. And based on this observation, people use often some kind of variational approach. So basically, imagine that you are looking for the ground state of a system. You don't know exactly what is the wave function of your system, but you know somehow the Hamiltonian, and you have a family of trial wave functions which will depend on a parameter kappa. Essentially, for example, you can think of a bag model. You will think of the nucleon as a bag with quarks inside. You have some kind of energy density inside the bag, and of course, you try to find the situation that will minimize or make the system stable. So if the system is too small, you will have too much kinetic energy. But if the system is very large, you can have low kinetic energy, but you have a lot of potential energy because the bag is super large. And you're trying to find the configuration that's kind of find the best compromise between kinetic energy and potential energy. So that's basically the same idea here. You have a system that's a state that will depend on certain parameter that basically gives you an idea of the size of the configuration. And you can move essentially the operation of changing the size from the state to the operator here. And if you work with the stationary state, again, so a state that would be an eigenstate of energy, then for a stable configuration, well, you will require that at the equilibrium situation would be that if you try to inflate the system, well, it will tend to go back to this equilibrium situation, and if you try to compress the system, it will go in the opposite direction. So basically, the equilibrium situation is when you have a perfect balance between kinetic energy and potential energy. So you have this kind of you look at how the energy varies with the parameter kappa, and you impose that this derivative is zero. So you extremize the energy dependence with respect to the size of the system. And if you look at the thing that you have here, you basically can convince yourself that it's nothing else than the time derivative of the generator of dilatations. So it's another way of looking at the thing that we have seen before, and also clarifies what the Virial theorem is essentially how the system reacts if you impose either a dilatation of the system, which can increase its size, or compression of the system. And in the stability, in the case of a stable system, you should be at an equilibrium point where either you go compression or dilatation. Basically, the system tries to go back to its equilibrium. So the derivative should be zero. It's an extremal point. All right, it's somehow clear so far. No questions. Okay, so that was for point particles. When we move to field theory, well, we simply have to generalize not to a finite or discrete number of particles, but a continuum. So basically, you replace the momentum of each particle by the density of momentum, and the density of momentum in the continuum is described by the 0I component of the energy momentum tensor. And the position operator, well, now becomes just a variable, position variable xi, and you sum over all the particles, which here correspond to summing over all infinitesimal volume of all space. And so the value g in the continuum is just the integral of this product, in some sense, of the momentum density by the position. Something that is already known for quite some time. So you do it originally in that book. It was in the classical field theory, but of course in quantum field theory, just similar. It's the same thing. It's just now that the energy, the momentum density becomes an operator. So if we apply exactly the same game as before, we would need to consider the time derivative of this operator or this quantity. And the only thing that depends on time is in the field theory is the energy momentum tensor. So look at the time derivative of the energy momentum tensor here, and x is just a parameter, so it has no time dependence here. And you can transform the time derivative as a four-dimensional derivative, so four-dimensional divergence, and then you have to compensate for the spatial divergence that wasn't there to begin with. And what happens is that, well, the four divergence of the energy momentum tensor is what defines somehow the density of force, the covariant force acting of a small volume in space. And for the second term, while you use integration by parts, as usual, you assume that you have no contribution from the boundary of the system, which and this term can then be written simply as the trace, the spatial trace of the energy momentum tensor. So you have these two terms. And then in the classical field theory, you just take the expectation value, sorry, the average over time. So you say the average over time of this quantity is 0. So I can relate the average over time of this term with the other term. And if you do quantum mechanics in the stationary states, it's just the quantum average as usual. But the formula is very similar. And if the system is isolated, it means that there is no external forces and all the internal forces balance each other. Well, basically the right-hand side is 0. And you conclude something very interesting is that for a continuous system, when you have the energy momentum tensor and you look at the spatial component, you trace over the spatial components, you integrate over all space, and you consider either the time average or the average in a stationary state. You should get 0. So it's a kind of stability or equilibrium condition. And this again can be understood in terms of dilatation. So it will be probably a bit more clear in the next slide. So what do you do? So for example, imagine that you have a system with a certain size, and then you make a dilatation of your system. You just increase all the coordinates, and you're interested in how the energy changes in your system. Well, if you increase the size of the system, there is some work that is involved, and so the variation of the energy of the system is basically related to the work that you exert or is exerted by the system, depending on how you look at things. On the other end, the variation of the Hamiltonian is due to a dilatation. So it's basically, you can get it quantum mechanically by the commutator of H and G for an infinitesimal dilatation. And this is nothing else than essentially proportional to the time derivative of this generator of dilatations. And if you combine these two, you can express essentially the work. The variation of the work is essentially related to this quantity that we've seen many times now, times the little variation or the little scaling factor, if you wish. Now, if you write explicitly in terms of the field, so we get the time derivative of the momentum density here that we can understand as a local force in a sense. This is a density of momentum. If you differentiate the density of momentum, you have a density of kind of local force. Then you decompose into two parts. A part that involves the force, which involves also the motion of the system, and the trace of the stress tensor that we already seen before. The first term here, the density of force, can be understood as essentially the force that is coming from the outside of the system. So it's the external force that is attributed to the system. Just imagine that the system is in an external potential. Well, the external potential would be the source of this force over here. Now, if you do not have external potential, you still have some forces that exist in your system simply because you have pressure forces inside your continuum. And those pressure forces are indeed described by the stress of the stress tensor. Indeed, if you look in the generic form of the stress tensor, energy momentum tensor in a relativistic context, you recover here, you find here the T0I component, which is interpreted usually as the momentum density. That's what we have used here. But the Tij component is what is described the stresses, so all the pressure forces on the system, and in particular on the diagonal, you get the normal stress, so the stress in the x direction, the stress in the y direction, z direction, and if you sum over all the stresses, you are basically looking at the isotropic pressure inside your system. And so the Virial theorem basically tells you that for system at rest, the virtual work that you would have if you try to either compress or dilate your system around the equilibrium position is exactly zero. That's basically what defines the extreme, so essentially the equilibrium configuration. So clearly, the Virial theorem has to do with spatial dilatations. Now, when we work in the relativistic context, we like to think in terms of space and time. So instead of looking at just spatial dilatations, we can also look at space-time dilatations. So if we do space-time dilatations, well, we can basically generalize what we had here, the value of G, which was this. So this is kind of a special scalar product, well, into something more covariant. So you have a four-dimensional scalar product here between the full energy momentum tensor now and the full four-vector position X. And if you look at the time components of this is called the dilatation current. It will define the dilatation density, and then you integrate over a whole space, you get the dilatation charge, that we call D. And if you use really the definition, you will see it's nothing else than the value of G that you had before, and an extra term, which is just the total Hamiltonian times the time coordinates. Probably it's a bit too detailed here, but what I want to say here is basically that you can play a little bit with the math and calculating all the commutators and so on, and you get the key formula, which is this one. So how can we understand this? Essentially, the left-hand side tells you how the form momentum is affected or changes when you apply a dilatation, a space-time dilatation. So dilatation in the four direction in space and time. And the result is two terms. The system is changing, so you do not have rescaling symmetry. So basically, you break, the system is not symmetric under dilatation. You have two contributions. So one is proportional just to the original form momentum. So it just says that how the form momentum change is just proportional to itself. So it's a rescaling of the form momentum. Okay, that's fine. But then you get an extra term, which comes with the time derivative of this charge, which somehow tells you that you break the dilatation symmetry. But that applies only to the component mu equal to 0, so only to the Hamiltonian, the energy of the system. And now if you take the expectation value of this relation in the stationary states, well, and you take the component mu equals 0, well, you can then relate the expectation value of the temporal rescaling, essentially that how the energy is rescaled by a space-time dilatation, and say that, oh, that's the same as the expectation value of the dilatation breaking, which you can decompose into two parts, thanks to this relation here. Well, one is the breaking due to in the temporal direction, and the other one is the breaking in the spatial direction. And you see that the expectation value of the Hamiltonian appears on both sides. They cancel, and at the end, you get again that's the Virial theorem. Even though you consider not three-dimensional dilatation, but four-dimensional dilatation, the end result is still that the expectation value of dg dt is equal to 0. So only the spatial part brings new information. The temporal part just basically cancel on the left and the right hand side. You do not gain any new fundamental information from it. So basically, temporal dilatation doesn't play a role in the Virial theorem. It's really information about how the system scales, but scales in in space. So maybe it's good to have a quick sum up of all the things that I've said. So I understand that there are many technical details, but I hope that you have at least a rough idea of what's all about. So basically, what is the Virial theorem? The Virial theorem is a statement about the mechanical equilibrium of the system, stationary state, under dilatations. Stationary states must be in mechanical equilibrium, and so if you apply a dilatation, change the size of the system by hand, well, the variation of the energy at the equilibrium should be zero, because you're really at external configuration. And the Virial theorem, it provides at the end an equality between average values of quantities at rest. So for example, how to relate the average kinetic energy to the average potential energy. It's a kind of balance between the two types of energy, but this balance depends on the type of potential you have. And you need to have the system at rest for it to be well defined. And also, I do not necessarily require the system to be closed. It could be an open system where basically, it's a closed system, but a system that is not isolated, that can have external potential. The Virial theorem applies. For example, you can imagine an electron in a Coulomb potential. I can apply the electron is bound to the nucleus. I do not need to care about the nucleus. I just need to know that the electron is the Coulomb potential. I can apply the Virial theorem in that situation and say that basically the average kinetic energy of my electron is related to the average potential energy of the electron, and I do not need to worry about the source of the potential. So it's something that is very useful in practice, in calculations. Well, I will skip that part. All right, before I move on to the question of the mass, which is another kind of related topic, is there any questions or things that I should maybe come back a little bit more in detail or just repeat?
Hi, Professor. I have a question, but yes, I can answer you later. But can I apply the Virial theorem something like to test an effective model, just like to see if I have a causality violation or something like that?
Okay. Okay. So for so for effective models, definitely yes. I don't see any reason why you can't use it, and we haven't used at any point the fact that our description is fundamental or not. So you need just a description, and you know how to write, for example, the associate some kind of momentum position to the particles, or kinetic energy, potential energy, and that should be fine enough. Now, regarding causality issue, I don't think that we can say anything about it. All we can say with the Virial theorem is that if you consider a system and you know that the system is bound, then the fact that the system is bound implies necessarily, due to the scaling properties of the way the system must behave under dilatation, which is a reflection of its equilibrium, gives a relation between the average kinetic energy and the average potential energy. But it doesn't, I don't think it tells you anything about causality.
Okay, thanks.
Other questions, comments, complaints? All right, well, doesn't seem so. Don't be shy and don't eat anybody. I've already eaten. Okay, so let's move then to the question of the mass, which is also, I think, a very interesting topic. Not necessarily very easy because there are a few concepts, but it's good because it's really a fundamental thing that we may at some point worry about. So what is mass? Well, big question. In in special relativity, we are told that, oh, well, you have the form momentum, you can define the form momentum of a system of particles and so on, so the total energy, the total momentum. And if the system is free, so there's no external force or potential or whatever, well, you just calculate the square of the form momentum is the Lorentz invariant quantity, and the quantity that you obtain is what you call the mass. Okay, fine. So clearly, by the definition, it's Lorentz invariant quantities. So that's nice because we think of mass. So, well, the modern version of mass is understood as a property that is intrinsic to the system. So it should not depend on the observer. It should be a Lorentz invariant quantity. But if you look at this definition, well, clearly, the concept of mass cannot be additive. Because if you have a system of two particles, the total form momentum is the sum of the two form momenta. And if you take the square of the sum of two form momenta, well, you have also the scalar product, for example, between P1 and P2 that changes. Maybe I should have written this somewhere. Okay. So essentially, if you have P1 plus P2 and everything squared, you will have P1 squared plus P2 squared plus 2 times P1 scalar product with P2. So P1 squared would be the mass squared of the first particle, P2 squared the mass squared of the second particle, but then you have an extra contribution, and then you see that just adding masses doesn't work in special relativity. So what you can add is actually the energy. That's always true. That's our assumption, that you can always add the energy. It's only at the end that you take the square of the total form momentum and get the final mass of the system. That's how we can somehow understand that, for example, the mass of a bound state is not necessarily equal to the sum of the mass of the constituents, because you have also interaction, you have kinetic energy, and all forms of energy also contribute to the mass of the system. So how to relate to the notion of mass? Well, basically, we can massage a little bit this relation, and if we are working in quantum mechanics, quantum field theory, well, that would be an operator relation. And then we can consider, for example, the expectation value in momentum eigenstate to simplify the discussion. So I can take the expectation value in the momentum eigenstate of this line, and I can massage it in this form. So essentially, I have the PP that is formally infinite, but okay, we can play as a physicist as if it was a good number. And then I just put one factor of m in the denominator here. And since P is an eigenstate of the total form momentum operator, I can pull out one of the operator P to replace it by the eigenvalue P mu. And now I have P mu over M. This defines just the for velocity, the center of mass for velocity of the system. And so I can express equivalently the mass of a relativistic system as the expectation value of the form momentum contracted with the for velocity of the system. And if I consider the rest frame of the system, well, the for velocity just gives me 1, 0, 0, 0. So just the temporal component is non-zero, which means that I just have the Hamiltonian component. So in other words, from this point of view, we can really understand the mass as the energy of the system in the rest frame. So you would say, oh yeah, that's okay, energy in the rest frame is not Lorentz covariance. Well, just say that in the rest frame, the expectation value of the energy of the system is the same thing as the mass. And if you go to a moving frame, well, you should not take the expectation value of the energy, but you have to take the scalar product of the form momentum operator with the for velocity of the system. And that one is Lorentz invariant, and in the rest frame, it has exactly that structure. So there is nothing wrong with thinking and defining the mass as the rest frame energy, is something that makes sense, just like you would define, it's very similar to proper length, proper time, etc. You know that time is a frame-dependent concept, but proper time is frame-independent because you define proper time as the time experienced by the particle itself. So basically the particle as if it were at rest, and we define this Lorentz invariant quantity. Here's the same, the energy at rest, you can see it as a proper energy or the proper inertia of the system, and from this point of view, it's really a intrinsic Lorentz invariant property. And the nice thing about it, since it's an energy, is that you can decompose the energy in terms of energy components like the kinetic energy, potential energy of subsystems A, B, C, whatever, and then you can define really a decomposition of the energy. And so when we want to talk about mass decomposition, well, naturally, it can only be understood as a decomposition of the energy in the rest frame. And then you can write it in the covariant form this way. So we can take an example, for example, the Dirac theory for a Dirac particle in external potential. You would have the usual kinetic energy, so alpha dot p. So alpha is the Dirac matrix, alpha x, alpha y, alpha z. You have a rest mass energy, the mass term, with the beta matrix here. And then you can also have a potential energy with some potential that is a certain function of position r. And the Virial theorem, if we apply the thing that we have said before, is that, well, for the bound system, or the stable configuration, you can relate the average kinetic energy to the average potential energy if the potential is basically some kind of power of the position. That's often what we consider. It's not the most generic case, but in that case, it's very simple. And based on this Virial theorem, just say, okay, for stable configurations, so bound states, you can essentially replace formally the kinetic energy by some multiple of the potential energy, and you can, instead of solving that problem, you can solve an equivalent problem for bound states, where you express the full energy as the rest mass energy and the potential energy, and you don't have to worry about the kinetic energy. So clearly the Virial theorem is often used in practice because it simplifies the expression. This is simpler to calculate than with the kinetic energy, but it doesn't mean fundamentally that there is no kinetic energy in the system. We have used an equality between the expectation value of two quantities, so the kinetic energy, the potential energy, to re-express something in a simpler way, but it doesn't mean that we have really eliminated the kinetic energy. So when we use the potential, when we use the Virial theorem, it's really a nice trick, but it shouldn't. One has to be careful that it may change the way you think of the energy content of a system. So since we are interested, for example, in the mass of a nucleon, we will consider then an isolated nucleon, an isolated system in a stationary state, and the system is at rest. So by definition of mass, the mass of the system is just the expectation value of the energy of the system in the rest frame, so the expectation of the Hamiltonian, and that should be the mass of the system. That's often how things are calculated, for example, the mass of an atom or other things like this. On the other hand, you have the Virial theorem, that tells you that the expectation value of you can also relate the expectation of the Hamiltonian will be equal to the expectation value of the dilatation operator. That's essentially the trace of the energy momentum tensor here. And if you combine these two, well, you would conclude that, well, you could express the mass of the system in terms of the trace of the energy momentum tensor. And so since the trace of the energy momentum tensor is a Lorentz invariant quantity, forget about the volume integral here, well, people were very happy and say, oh, that's the natural definition of mass, should come from the trace of the energy momentum tensor. Well, it's true, but we have seen that to justify it, we really need to consider the state. We do not have any operator that relates the trace to the mass. It's only in terms of expectation value for a stationary state at rest that this is true. So people that really like this kind of expression propose a decomposition based on the trace of the energy momentum tensor, and that's what we call the trace decomposition. There's another group of people that somehow are not totally happy with that, but are not do not want to get rid of it completely. So what they propose, you say, okay, let's consider the total energy momentum tensor and use the symmetry of the Lorentz, so the Poincaré group. So essentially you have Lorentz symmetry and translation symmetry. And what you can do when you have a rank 2 tensors, that you can always decompose. The tensor is symmetric here. We take a symmetric rank 2 tensor. You can decompose into a traceless part and a pure trace part. So that's fine, because you will have the trace that appears there, and then that's the rest. And you know, because of the symmetry, that the trace part doesn't mix with the traceless part of the Lorentz transformation. They don't talk to each other, and even under renormalization and all that, they don't talk to each other. They are really independent. They are different, irreducible representation of the Poincare group, which is convenient for a theorist. And now, if you take the 0,0 component here of this expression, and you take the volume integral and expectation in a stationary state at rest, well, the left-hand side would be just the expectation value of the total energy, which for a stationary state at rest is just the mass of the system. On the right-hand side, you have 1/4 of the volume integral of the trace. For a system at rest, it's just 1/4 of the mass, just like we have seen here. And then the part that comes from the traceless part would be the rest, which should be 3/4 of the mass of the system. So some physicists like to start with this decomposition, saying, okay, just by Poincare symmetry, it's nice to decompose the energy into traceless and a trace part. And the Virial theorem implies that the trace part should be 1/4 of the mass of the system, while the traceless part should be 3/4, irrespective of the details of the interaction and so on. That's something that is very general. Maybe some of you have heard about the old electromagnetic theory of the electron. So about more than 100 years ago, Lorentz and company trying to build a model of an electron as kind of a ball of pure electromagnetic energy. And according to classical mechanics, the stress tensor for the electromagnetic radiation is traceless. And so by calculating the energy in a sphere somehow, they try to match to get a model for the electron, and they had always a problem that was a factor 3, 4, 4, 3, depending on how you phrase the question. And this is really to the fact that they had a traceless quantity. And Poincare solved the problem later by introducing what were called the Poincare stresses, that were new forces, electromagnetic forces, that were there to maintain this mechanical stability of the system, which was something that was not considered here. And this added the missing 1/4 of the mass to get the total system. So we see that this contribution is very important and is related to the stability of the system. But one thing that I would like to stress here is that we started with the energy of this, so the form momentum of the system is, so the mass of the system is defined with respect to the form momentum operator. And the form momentum operator is the special integral of the 0 mu component of the energy momentum tensor. And when you calculate the trace of the energy momentum tensor, you involve the component Tij. Tij never appears in the form momentum operators. So it's really weird, in a sense, to say that the trace of the stress tensor has gives you information about the mass of the system, because from the very beginning, the mass operator or the energy operator doesn't know anything about the Ij components, just the 0,0 component of the energy momentum tensor, but not the Ij component. It's only because we use the Virial theorem and we consider equality between quantities in expectation value that you can transform one thing into another and have the impression that the trace of the energy momentum tensor tells you something about the mass. So we arrived at basically the picture that we have. So either you like very much the trace expression, so the relation between the trace of energy momentum tensor and the mass, which can, I stress again, this relation holds only at the level of the expectation value. It's not true in general. Then you can decompose into two terms. I will not go into the details. If you prefer to say, no, it should be really the energy in the rest frame, then you will naturally decompose into three terms. One would be the energy of the energy of the gluons. If you talk about the the nucleon. Then you have the kinetic energy of the quarks, so it's the total quark energy minus the mass contribution, and then you have the mass contribution of the system. So you have 3 terms, you just need 2 independent inputs because of your sum rule, and then that's how you can solve. I won't go into the details here. And then there are people that like very much a decomposition to traceless and trace parts. So they really are using the Virial theorem, and they say, oh, we should not decompose into 3 terms, but we should decompose into 4 terms. But when you look at those 4 terms, instead of having 3 independent inputs, you have only 2 independent inputs, which means that you have a relation between the 4 contributions that is not fixed by the dynamics at all. And the relation is really the Virial theorem, which allowed you to connect the quantities together. So just in a graphical way, when people talk about the mass decomposition, you may see pie charts of this form, and you have kind of 3 different group of people. The ones that like the trace of the trace of the energy momentum tensor, because this is related to also space-time dilatation, as we have seen before, and have the feeling that anything that has to do with mass has to do with space-time dilatations. So they will decompose into a quark mass term, and then something that has to do with the anomalous behavior under dilatations. Complicated stuff, I will not go into the details here. There's another group, so that's basically the group which I belong to, prefer a 3-term decomposition. So just like in the classical theory, you can transpose it in the quantum mechanical theory, where the total energy is just the kinetic energy of quarks, the kinetic energy of gluons with their interactions, and the quark mass contribution, and you sum everything and you get the total mass of the system. And at no moment you ever use the fact that the system is stable. You just need, I have an eigenstate of energy, and I do not use the Virial theorem. I do not change the meaning of the operators. I do not use any identities that are valid only at the expectation value level. And then there are those who prefer 4-term decomposition because they still want to have some information about the trace anomaly. And in that case, they somehow slice up the gluon kinetic energy into 2 parts, the parts that will be traceless, like in the classical theory, so they would call it, for example, the classical gluon energy or whatever, and then the rest would be only 1/4 of the trace anomaly. But this decomposition is motivated by the Virial theorem, and if you do not have the Virial theorem, there is no really reason for doing, or motivation or justification for doing so. So maybe it's good that, or it's already late, we can go to the quick conclusion. So I talk about 3 points in this presentation. So the first is I try to summarize the meaning of what is the Virial theorem. So essentially it's the relation, a statement about some kind of expectation value between kinetic energy and potential energy, roughly speaking. What is the physical meaning? It's basically a statement about the mechanical equilibrium under spatial dilatation. So if you want a system to be stable, it's really when you try to increase or decrease its size in space. And what is the relation to mass? Well, in principle, it has nothing to do with mass because the mass is the energy in the rest frame. There is no connection with the TII component, so there's no relation to the work done when you try to increase the size or decrease the size of the system. So you have actually 2 sum rules. There's one sum rule, which is the mass sum rule. So the total energy at rest is the mass of the system by definition. And then you have another sum rule, which basically tells you that the total pressure volume work should be 0. So you have a system at equilibrium. But now, of course, since this is 0, you can take linear combination of those 2 relations. The left-hand side would be always the mass. So you take, for example, the left-hand side and then take alpha times the right-hand side. I can always decompose into more than the necessary term and define many different kind of trace decomposition and define a kind of generalized form of mass decomposition, which relies on the Virial theorem. And depending on the parameters that you use for the linear combination, you can recover the trace decomposition or what is called the G decomposition. What is their physical meaning? Well, I will be a little bit reserved concerning that point. All right, thank you very much. We have maybe time for a couple of questions, so please don't hesitate. And thank you for listening.
Okay, thank you very much for such a nice seminar. I guess everybody learned a lot. Do the audience have some questions? Perguntas? So there is one question in the chat. Which Feynman diagram could be associated with the trace anomaly?
Okay, so the so for the trace anomaly, you can maybe you can see things on the blackboard over there with right click. The problem in QCD is that you always have non-perturbative information. So it's a Feynman diagram, but with blobs that describe boundaries. So imagine that you have a proton here, and then you look for a certain contribution. For example, you have a gluon inside the nucleon, and you insert an operator here, you measure something, and the operator that you will put here is the anomaly operator that would be beta over 2g, the square of the field strength tensor. So that's one way of calculating it, and you have also the contribution from the anomalous mass contribution. So we have a quark here, and the operator that you insert here is the anomalous, so the anomalous mass dimension of the quark that you can calculate. QCD is a bit complicated. It's usually non-perturbative information. So usually either you try to calculate that using lattice QCD, or you try to extract it from some kind of experiments that will be sensitive to an operator like F squared. So there are some arguments. For example, if you look at electroproduction of depth size, so heavy quark on quark downstate on the nucleon, and you look at this process close to threshold, that should be very sensitive to a local, should be very sensitive to the trace anomaly, because of the large mass of the quark. Essentially, you are probing the system with an operator that is very close to F squared. So that's why there's a very intense program now trying to get as close to threshold as possible and try to get information about that trace anomaly contribution. So it's definitely an information that's very interesting. Whether it really represents a contribution to mass or not is still something that the community has not agreed on, but it's something that we can measure. It has definitely some very interesting information about the system. If you want a fully perturbative calculation, you should change the models. For example, recently we have had a paper in the scalar diquark model. In the scalar diquark model, you can really calculate everything at one loop order. At one loop order, you can also calculate explicitly the trace anomaly by just diagram like this. We have a further interacting via a boson, the scalar diquark model. And all the sum rules are explicitly satisfied, and also the Virial theorem is defined, then you can get it explicitly. But really what you have to do is to insert, let's say, F square operator and side by side operators, so the scalar operators in your Feynman diagrams. A kind of an extra Feynman rule that you have to embed in your calculation.
Okay, thank you. Well, I guess...
I have another question.
Okay, please go ahead.
Usually we see Virial theorem in the context of statistical mechanics. So historically, where that came the idea of use the Virial theorem to calculate the masses?
So for statistical mechanics, it was basically already when doing let's say the ideal gas, etc. Maybe a little bit before as well. For the mass of a system, it started about the same time when people started to apply they started to look at space-time dilatations. When people did that was already, I think, around. Okay, maybe we have the. Let me see. Yeah. Okay. Let's say the first time that people mentioned the trace to and the connection to mass was in the late 70s. So I think this is one of the very first paper, if not the first paper, where this was clearly considered. So historically, that's the first way to access the mass, but just as a sum of expectation value. No, how these things are really related to mass is a question. Only the sum is really the mass numerically. That's fine. And the other decomposition, so the G decomposition, was in 1995 essentially, and then only more recently that's there's been some rediscussion of this kind of stuff. But for the trace, it's late 70s.
Okay, thanks.
All right. Perhaps I have a question. Can we go to the, not the last one, but the one before the last one?
This one?
Yes, this, yes. So, well, perhaps two questions. So how does this energy decomposition in the center relates to that old result that the parton distributions, when the partons were the new thing, they went to look into the partons inside the proton, and they saw that the quarks would carry only half of the longitudinal momentum.
Mm-hmm. Yes, that's a good question. So so the part of the camembert here are really the expectation of the value of the energy in the rest frame of the system. When you probe in experiments the structure of the system, you're usually considering a system frame, right? So the Feynman picture where the nucleon is moving with almost the speed of light, and you are mostly sensitive to the fraction of momentum carried by the partons. And so the momentum fraction that you mentioned, that's basically for the nucleon, almost half of the momentum is carried by gluon and almost half is carried by the quarks, is in the contribution that's the term A here. If you wish, A is nothing else than the expectation value of the momentum, the light cone momentum fraction X for the quark, and then you have the same for the gluon, and then the first A quark plus A gluon equal 1 is the momentum, the light front momentum sum rule. But now those are, so the light cone momentum fraction are defined with the component T++. If you look at the energy momentum tensor and look at the local operator, so not non-local, but all the fields are evaluated at the same point, you can parameterize the energy momentum, the matrix element of the energy momentum tensor in terms of form factors, just like the electromagnetic current are described in terms of Dirac and Pauli form factors. Here you can define energy momentum tensor or gravitational form factors. And when you measure the momentum fraction, you can give a constraint on some of the form factors, and typically the form factor A. The information that you need now is information about the form factor C bar, which enter the decomposition, and is related to the trace of the system. It can also be related to the expectation value of the scalar constant, so psi bar psi condensate. So this kind of term here can be also related somehow to C bar Q. And so really we use the information about the decomposition of momentum and use the covariance of the fact that we can describe the full energy momentum tensor in terms of the same form factor. It's really a covariant description to infer something about how the energy is decomposed in the rest frame. So that's the nice stuff. We use form factors to say, I have information on the light front, high energy or fast-moving nucleon, and thanks to Poincare symmetry, I can say something about the energy in the rest frame. And that's the result, essentially.
I see. Thank you. Well,
so the fact that you have almost 50% decomposition of the momentum into quarks and gluon is somehow reflected here. You have basically 54% of energy of the gluon and 46% of the quark. So it's very close to the momentum fraction decomposition.
Right. Okay. And the other question is, it's more speculative. What if, when we talk about this gluon part and the quark part, what if they have different sizes? Okay. Well, you think you do dilatations, but maybe they respond differently because they have different, perhaps, scales or sizes.
So your question is about why do we understand why we have this kind of sizes for the different contributions?
No. Sorry. I mean the physical size in the proton.
Okay.
Maybe the quark field is not as well localized, or is more localized in a smaller space than the gluon field.
Yeah, unfortunately, I don't have a slide prepared here, but basically, yes. When it comes to the size of a system, you can define many types of sizes. So you can define the size as the distribution of electric charge, and that's basically what we call the proton radius, but that's basically the charge radius of the proton. It doesn't mean that if you take a proton, the energy has the same size. You can also define the energy radius in the rest frame. And if you do so, what we have observed with the current knowledge of the gravitational form factors, that basically the energy radius is larger than the charge radius, which indicates that basically thanks to gluons, so the quarks seems more concentrated to the center, and then the gluons somehow occupy a larger volume inside the system and gives a larger energy radius. Some other people like to define not the radius of the T00 components of the energy, but prefer the radius of the trace because of the trace decomposition. And then in that case, they get also yet a different radius. So depending on which quantity you define as a spatial density, you will have different radii. What is very complicated is that if you are really interested in the radius of the whole system, you should have the full information about both the quark and the gluon content. And so far, most of the experiments give only information about the quark part, and for other quantities, only the gluon part. And when people talk about, recently there's been some extraction of some gravitational form factors that are assumed to be for gluons only, modulo some approximations, and then you define a radius based on it. Well, the meaning of that radius is a bit weird because it's not the radius of the whole system, it's only the radius of the gluonic parts. And if you pay attention, there should be additional contribution. For example, you have also contribution from another form factor that is C bar. And since the sum of quark C bar and gluon C bar is 0, you do not see it in the sum, but when you decompose into quark and gluon, you have to take that contribution into account if you want to define a meaningful radius associated with quark or radius associated with gluons. And the problem is that experimentally, we do not have yet much information about those C bars. And some people prefer just to ignore it and say, okay, at the end, it doesn't matter. But since you do not have the full information and you want to make a big claim, you better have to be precise in how you define your notion of radius. And you cannot conclude something, I would say, strong if you have a small radius or large radius if you do not have properly included all the contributions.
Okay, thank you very much. Any other question? No. So I guess we thank Cédric again. It was a pleasure to talk with you again and have this nice seminar. Hope to see you.
Thank you very much.
Future.
Take care and see you another time. Thank you very much.
Bye
Have
bye.
a good day.